What are weights in AI models? In this blog post, What are weights in AI models and why they matter for accuracy, we will unpack what weights are, why they're central to every prediction your model makes, and how to manage them well in production. At a high level, weights are the dials an AI model turns to convert inputs into outputs. During training, the model learns where to set those dials so predictions match reality. When you hear that a model has billions of parameters, those parameters are mostly weights, numbers that control how strongly different signals influence the final decision. Think of weights like knobs on a mixing console. Each input feature, a pixel intensity, a word embedding dimension, a sensor reading, flows through, and the weights amplify, dampen, or combine them. Get the settings right, and you've got a hit track. Get them wrong, and it's noise. What exactly are weights? Formally, weights are numeric parameters learned from data. In a simple linear model, the prediction y equals wtx plus b, where w is the weight vector and b is a bias term. In deep neural networks, the same idea repeats across many layers, with weight matrices or tensors connecting neurons or attention heads. Different architectures use weights in different ways. Linear layers, weight matrices map input vectors to output vectors. Convolutional layers, small weight kernels slide over inputs to detect patterns. Embeddings, weight tables map discrete IDs like words or items to dense vectors. Attention, query, key, and value projections are weights that control how tokens attend to each other. Biases, per neuron offsets that shift activations. The technology behind learning weights. The main technology behind modern AI training is gradient-based optimization. We define a loss function that measures how wrong the model's predictions are, and we use gradients, computed via backpropagation, to nudge weights in the direction that reduces the loss. Forward pass, compute predictions from current weights. Loss, compare predictions to ground truth, e.g., cross-entropy, MSE. Backward pass, compute gradients of the loss with respect to each weight. Update, apply an optimizer, SGD, atom W to adjust weights. Backpropagation uses the chain rule from calculus to propagate error signals from the output layer back through each layer, accumulating gradients efficiently. Optimizers scale and combine those gradients to make progress stable and fast. Regularization, dropout weight decay, and normalization, batch layer norm, help keep weights well-behaved and prevent overfitting. Precision, size, and performance. Weights aren't just numbers. Their data type and layout matter for speed and memory. FP32, full precision, slower and larger, common in training. FP16, BF16, half precision, faster with tensor cores. Standard for mixed precision training and inference. INT8, INT4, quantized integers for efficient inference with minimal accuracy loss when calibrated well. For large models, choosing the right precision can cut costs dramatically. Quantization-aware training or post-training quantization lets you compress weights while preserving accuracy. How weights shape model behavior. Small changes to weights can shift decision boundaries or the content a generative model produces. In classification, weights define the hyperplanes that separate classes. When it comes to vision, convolutional filters become edge detectors or texture finders. In transformers, attention weights, via learned projections, decide which tokens influence each other. Because weights encode the model's knowledge, versioning and reproducibility are critical. The code and data matter, but the weight file is the thing you actually deploy. Practical steps to manage weights in production. Version artifacts, not just code. Store weight files in an artifact registry with semantic versions and immutable digests, e.g., SHA-256. Track lineage. Record data snapshots, training config, optimizer state, and seed to reproduce weights. Quantize for inference. Benchmark FP16 and INT8. Validate accuracy drift on a holdout set before shipping. Secure the supply chain. Sign weight files, enforce checksums at deploy, and restrict who can push to the model registry. Canary and shadow deployments. Serve new weights to a small slice of traffic or in shadow alongside the current model. Compare metrics before full rollout. Monitor live. Watch input drift, output distributions, latency, and error rates. Set alarms on unexpected shifts that may imply weight issues. Reading and updating weights in code. Here's a minimal PyTorch example that shows weights changing during training. This loop computes gradients and updates weights with SGD. After training, the learned weight and bias will be close to 3 and 2. Common pitfalls and how to avoid them. Overfitting. Weights memorize training noise. Use regularization, early stopping, and more data. Exploding vanishing gradients. Weights fail to learn or blow up. Use residual connections, proper initialization, and normalization. Data leakage. Weights learn future information. Strictly separate train validation test and respect time order. Unstable deployment. Weights differ between training and prod due to preprocessing mismatches. Lock preprocessing and feature schemas with tests. Silent regressions. New weights degrade niche cases. Add slice metrics and canary checks before rollout. When and how to fine-tune weights. Fine-tuning adapts pre-trained weights to your domain with less data and compute. Full fine-tune. Update all weights. Best accuracy, highest cost. Adapter or LoRa. Add small trainable modules. Freeze original weights. Efficient and reversible. Prompt or instruction tuning. Lightly adjust behavior with small parameter changes or additional tokens. Choose the lightest method that meets your accuracy and latency targets, and keep a clean path to rollback. How to evaluate the impact of new weights. Offline, compare metrics on a fixed benchmark and critical data slices. Run robustness checks, perturbations, adversarial cases. Cost and latency. Measure memory footprint and throughput across precisions. Online, run A/B or canary with guardrails. Watch task-level KPIs, not only model metrics. Key takeaways. Weights are the learned numbers that encode your model's knowledge. They're learned via gradients and optimizers. Their precision and layout drive cost and speed. Treat weight files as first-class artifacts. Version, secure, test, monitor. Use fine-tuning and quantization to adapt and optimize from production. If you're planning how to train, version, and deploy model weights at scale, a thoughtful pipeline pays for itself in reliability and cost. At cloudproinc.com.au, we help teams design robust ML workflows, from data to weights to production, so your models ship fast and stay trustworthy. Loading and saving PyTorch weights. LLMs self-attention mechanism explained. The autonomy of tensors. Get started with tensors with PyTorch. Build a Keras model for real projects.